All right, y'all, welcome to section 3.3, complex numbers. We're looking to simplify them, add them, subtract them, and multiply them today. And next section we'll do division and some other things too. But just to review, let's remember, what are the perfect squares? 1 times itself is 1, 2 times itself is 4, 3 squared is 9, 4 squared is 16, 25, 36, 49, 64, 100. It keeps on going. And if we need any higher numbers than that, then we can figure out what they are later. But that's what perfect squares are. And also we need to remember property here. You may or may not have learned it from Algebra 1. That is that the square root of two numbers times each other is going to equal the square root of the first number times the square root of the second number. Here you can see the multiplications on the inside, and here you can see the multiplications on the outside. They're just equal to each other, which is great. It's going to be very helpful. So for example, the square root of 8 is the same thing as the square root of 4 times the square root of 2, which is awesome because then we can actually take the square root of 4. We couldn't take by hand. You could ask a calculator what the decimal version is, but oftentimes it's actually mathematically a lot more useful to kind of like simplify it from here down to here, because you can take the square root of 4, which is 2. So you'll find often that kind of like simplifying fractions, there's like these have like square root of 8 and 2 times the square root of 2 actually have the same decimal form. You ask a calculator what the decimal version of both of those numbers are, and they're equal to each other. But just like simplifying fractions, the simplified version is going to be a lot more useful and also expected when it comes to like testing, quizzing situations, and on ALEKS. So let's figure out how we can simplify square roots. Here you can see the trick really is to find a perfect square factor of 50. Find a number that's on this list that is a factor of 50. It's both a perfect square and a factor. And that number, that magical number, is going to be 25. You write it first. Square root of 25 times the square root of so you have to figure out 25 times what is 50, and that's 2. So you can take the square root of 25, even though you can't take the square root of 2. And you can simplify this down to 5 square roots of 2. Again, what's the perfect square factor of 20? What number is on this list that's a factor of 20? It's 4. So square root of 4 times square root of 5 is 2 square roots of 5. Square root of 16, that's just 4. 4 times itself is 16. That's super easy. You don't have to be too complicated about that. Square root of 12 simplifies down. We have to figure out what is the perfect square factor. Everyone say perfect square factor. Yeah. Okay. So we've got square root of 4. That's 4 is the number on this list. 4 times 23 is 12. So square root of 4 times square root of 3 is equal to the square root of 12. And you can take the square root of 4, and that's 2. It's simplified. Square root of 100 is 10. Now, if you had done, if you hadn't realized that, you could say, well, square root of the perfect square factor of 100 is 25. And 25 times 4. So you could write this, if you wanted to, as square root of 25 times square root of 4, which is just 5 times 2, same thing as 10. It simplifies out either way. Square root of 24, you can see square root of 4 times square root of 6 is 2 root 6. All right, and now that you know that this imaginary, now that you know that this thing called an imaginary number, let me tell you what it is. This is new, and this is mind-blowing. It's an imaginary number. I is equal to the square root of negative 1. And we are going to spend like the next, I don't know, like 5 or 6 lessons talking about I. And throughout the whole thing, I'm going to dance around the sticky question of what is I exactly? Well, I is the square root of negative 1. You might say, Mr. Bergman, what is the square root of negative 1? I'm not going to tell you, and you don't need to know. You will never be able to you'll never be able to cut a piece of wood of length I, or square root of negative 1. It's not even on the number line. It's not a real number. It's a different thing. And there are applications for it, for sure, in physics, in quantum physics, in electricity, but not in our day-to-day life. You can't go to a bank and say, I would like to deposit $I or 10 $I. You can't. There's just no such thing as a real, it's just not a real number. We've got plenty of real numbers. They're all in the number line, and this is not one of them. But what we're going to do is we're going to move through, we're going to if we just accept that I is equal to square root of -1 and accept the fact that this is not a real number, it's some sort of completely different animal, then we can actually move forward quite a bit in our mathematics and our techniques. If you square both sides of this equation, you get I squared is equal to -1, and that's going to be useful too. So these are the two facts that we're going to really use and lean on. And then, and you can say, and then you can start, everything else apart from that is going to be like, well, okay, so what is I plus I? We'll call that 2I. What is I plus I plus I? 3I. And what is 3I divided by 3? I. Like, we're just going to be doing a ton of math, and we're going to move forward not answering the question of what is the square root of -1, because there is no real good answer. It's just an imaginary number. So if you wanted to simplify the square root of -48, like here we were simplifying these square roots, and if you wanted to simplify the square root of -48, you could split that up. And the absolute very first thing that you've got to do when you have the square root of -48 is split it up into the -1 and 48, because really this property does not apply for imaginary numbers. It only applies for real numbers. So you really can't move forward anywhere unless you are dealing only with a real number like 48. So split that up. You got the real part and the imaginary part, and then once you do that, you can say, oh, square root of -1. That's just going to be I, and we'll write I for the rest of it. Not knowing what I is, it's okay. You can dance around that question and just say the square root of 48 is going to be the square root of 16 times the square root of 3. If you had chosen the square root of 4. Both 4 and 16 are on this list. It's best to choose the higher number because it'll simplify more. Just like with fractions, like 50 over 100. When you simplify that, you could say, oh, it's 25 over 50. But you can really keep on going. It's simplify 5 over 10. Simplify 1 over 2. In the same way, you really want to pick the highest number you can to simplify it down quickly. Otherwise, you have to simplify over it a second time. But if you choose a high perfect square factor like 16, then 16 times 3 is 48. And this is equal to the square root of 16 times the square root of 3 times I. And knowing that I is the same thing as the square root of -1. So the answer is 4I root 3. And you can't measure your bed is not the length of 4I root 3. It's not on the real number line. It's a completely different number itself because there's that I in there. There's unwritten multiplication. 4 times I times square root of 3. Here, square root of -63. Well, the first thing you got to do is separate out the square root of -1 because this property only applies to positive real numbers. Real numbers, not positive. It could have negative numbers on the outside if you want. But on the inside of the square root, you got to have positive numbers. So square root of 63 times the square root of -1, that's just going to be I, and this is square root of 9 times square root of 7. Square root of 9 is 3, so it's 3I root 7. -72. You can see this is separate out the square root of -1, because 72 times -1 is -72. Then you got 36 times 2, or 6I root 2. -24. The highest first you can separate. You could do these two in 2 steps if you really wanted to. But I'm showing you more work so that you can see what's going on. And I'm just making one very small change and recopying. Square root of 24 times the square root of -1 is square root of 4 times square root of 6 times I, or 2I root 6. We like to put the radical last so that you can see that it's very clear when you write it this way that the 2I is not inside the root and the 6 is. If you were to put the 2I on the other side or the 6I on the other side, it wouldn't be mathematically wrong, but from a formatting and reading, if you're going to communicate your answer, sometimes, especially if it's handwritten, it's a little tricky to figure out whether or not the thing that follows the root is actually really in the root or not in the root. But if you write it out front, then it's very clear. This is outside and this is inside, no question about it. But mathematically, you could put it at the end if you really wanted to and would be correct. And on alex.com, you could put 2 on the outside and it could follow it and it would be able to read it. Just be careful that you've actually exited the radical. Square root of -84. factor out the root. Perfect square factor, the largest perfect square factor is 4. So square root of 4 is 2. Square root of 21 just leaves an I. Just leave it's 2i root 21. Negative 99. Take the square root of it. Well, if you wanted to simplify that, you'd get square root of negative 9. And then the largest perfect square factor of 99 is 9. So you put that first. Square root of 9 times square root of 11 is times I. 3i root 11. So the big idea is to replace negative 1 with I and do this as early as possible so that you can then use real number math rules. All right. Next, let's simplify square root of 10 times the square root of negative 15. Well, just using the big idea that we just had, we really can't do any kind of operations with a negative on the inside of a square root. So the very first thing you got to do is get the square root of negative 1s out of there. And now that you have the square root, I'm going to rewrite these as the square root of 2 times 5. 2 times 5 times negative 1 is negative 10. And 3 times 5 times negative 1 is negative 15. So I'm going to write them all out. You can see all of these apply here. Now, if you have the square root of negative 1 and square root of negative 1, that's going to be I and another I. And so it's I squared. And if you have square root of 5 times square root of 5, that's just going to be 5 here. And then if you have square root of 2 times square root of 3, those are the leftovers that don't really have pairs. So the radical doesn't disappear there. 2 times 3 is 6. Now, remember, I squared, this is another big fact that you have to remember and get used to, is that I squared is equal to negative 1. Everyone say I squared is equal to negative 1. Yeah, there it is. Okay, so if you have I squared, it's not, if you type in I squared into alex.com and say that's my answer, it's going to say it's wrong because you can simplify it further. Same thing on a quiz or just on a project or just in math generally. Don't leave I squared by itself because you can replace that with negative 1. The actual answer is negative 5 square roots of 6. Negative 6 goes 3, 2, negative 1. Negative 21 is 3, 7, negative 1. Pairs are 3. The 3 pairs very well, so the square root of 3 times the square root of 3 is just 3. Negative 1, that's I. 2, there's 2 i's, so it's I squared. And then the 2 and the 17 are left over, you get square root of 14. And then negative 3 root 14 is the actual answer. And this is a real number. It's not an imaginary number. Negative 18, negative 3, if you're multiplying these two together, you get 3, 6, negative 1, and 3 and negative 1. The square root of 3's pair, so they cancel out the radicals, and you get I squared is square root of 6. Negative 3 square roots of 6. All right, 3i times negative 2i times 5i. Well, you have 3 different i's. 2 of them will cancel out to get negative 1, and 1 of them will be left over. 3 times negative 2 times 5 is negative 30. And so negative 30 times negative 1 is 30. So that's just 30i. If you're going to multiply these together, I think the first thing to do would be to get rid of the exponent, distribute that exponent to everything, to all the factors on the inside. Negative 6 squared is positive 36. I times itself is I squared. And then you still have the 4i on the outside. Now, I squared is negative 1. So that's why the overall answer here is negative. And then 4 times 36 is 144, and you're left with the I. All right, so that's what that looks like. We can also solve. Let's review a little bit. Solving this, x squared minus 81 is equal to 0. You've got x squared is, you could, if you wanted to, actually add 81 to both sides, and then you take the square root of both sides. You get x is equal to plus or minus 9. Both positive 9 works here in this solution, and negative 9 works in both of these equations. Like negative 9 times itself is positive 81. So when there's two solutions, you've got to report both of them. People often forget that when you take the square root of both sides, you have to add a plus minus to indicate that there are actually two solutions. Let's check this out. Same thing over here. If you wanted to, you could just like undo operations, the subtraction, the multiplication, the squared, in that order to get what you need. So undo the subtraction with addition to 45, undo the multiplication to get x squared equals 9, and then take the square root of both sides, and you should get x equals 3. It's not even there. X equals plus or minus 3. I'm not going to write it. You can write it if you want. I'm out of space, honestly. 4x squared minus 24 equals 0. So 4x, undo the subtraction, bring with addition, undo the multiplication with division, undo the exponent with a radical. So when you take the square root of both sides, you get x is equal to plus or minus square root of 6. Undo the multiplication, undo the squared with a radical, you get x could be plus or minus 1. So that's all good. That's kind of a review. Now, what happens if when you take the square root of a negative number? What would that look like? Well, let's just change one little sign. This was x squared minus 81. Let's change that to x squared plus 81 equals 0. And you can see you got x squared is equal to negative 81. And when you take the square root of both sides, you get x is equal to plus or minus the square root of negative 81. Up until this section, you've been like, well, that's impossible. There's no solutions. Well, technically there are no real solutions. That's still true. But what is new is that the fact that there is now actually some imaginary solutions. Because when you can actually factor out the square root of negative 1, and then you get x is equal to plus or minus 9i. There are two solutions. Neither one of them are real. There are two imaginary solutions. Imaginary solution 1 is 9i, and imaginary solution number 2 is negative 9i. So let's take a look. Changing the subtraction to addition, you could undo the addition with subtraction. Boom, negative 45. Undo the multiplication, and then undo the exponent, and you get plus or minus the square root of negative 9. We know how to handle this. We can say square root of 9 times square root of negative 1. And what do you get after that? You get x is equal to plus or minus 3i. And you might say, well, Mr. Bergman, where exactly is that on the graph? You can't graph it. It's not there. The xy coordinate plane is, at least the one that we have. There are imaginary coordinate planes, but the one that we have only deals with real numbers. This doesn't even have a location on the graph. You can't find the x-intercept here because it's not real. It's imaginary. And we just have to be okay with that. So here, changing the subtraction to addition, you can undo the addition with subtraction, undo the multiplication with division, undo the exponent with a radical, and you get x is equal to plus or minus square root of negative 6. No biggie, because we can factor out the square root of negative 1, and we get x is equal to plus or minus I root 6. And what that means, it doesn't matter, because you can just say that's the solution. This is the imaginary number that when you put it back into the original, then and you square everything, multiply by 4 and add 24, you do get 0. And that's cool. Here, we change this positive 9 to negative 9, and all of a sudden you get x squared is equal to negative 1. So the two numbers that will satisfy this equation is a positive I and negative I. So there it is. What is a complex number? A number that is, and complex numbers get such bad rap. They're not really complex. They're just misunderstood complex. It's just like this is not a hard thing to understand, and that's not why it's called complex. That's just the name that someone gave some mathematician at one point. A number that has both real and imaginary parts. So for example, 1 plus 2i. These are not like terms. You cannot combine 1 plus 2i to get like 3i or 3 or something in between. You just have to say that it's one single number, 1 plus 2i. Here's another complex number, 3 minus 4i. They're not like terms. There's no variables. Remember, I is not a variable. I is a square root of negative 1. But you really can't condense it any further. So we're just going to consider these 0.5 plus 1.6i. Like you could have subtraction. The imaginary part would be negative here. You could have decimals. You could have radicals. But generally, a plus bi is the format of a complex number, a single complex number. How do you add these together? Well, you would combine the like terms. You can't combine negative 4 plus 2i, but you can combine the negative 4 and the 6. You get 2. You can combine the 2i and the negative 3i. 2i minus 3i is negative 1i. So there it is, 2 minus I. And you notice I'm writing it in a plus bi format. If you're going to take these two numbers and subtract them, this number minus this number, well, you can combine the like terms. The real terms combine to 4. The imaginary terms combine to 13i. And the final number is 4 plus 13i. It's really weird. I gotta pause and just say, it's probably really weird for you right now to think about something where the one number that's separated that has two different terms. And I get it, it's strange, but you can just like accept it and move on and say like, oh, if that's what addition looks like, this is what subtraction looks like. And then later on, this is what multiplication is going to look like. 8 minus 6 is 2. 3i minus negative 2i is going to be, here's the new thing. With subtraction, you can distribute the subtraction, just like you do with regular parentheses. Distribute the subtraction, this becomes minus 6, and this becomes plus 2i. Very important here. A lot of students forget this. Minus becomes plus. So this is 2 plus 5i. 5 minus I minus 3 plus 2i, and these combine to 2 plus I. So generally, if you're trying to, in order to add or subtract complex numbers, you want to combine like terms. But what if you're going to multiply? Okay, so here we go. If you're going to multiply these two bad boys together, then we got a FOIL. Because just like if this were a variable. Although it's not a variable, it's a number, but that's okay. The first terms is 32. The outside terms turn into multiply up to negative 80i. The inside terms multiply up to 12i. And the last terms multiply up to 3i times negative 10i. That's negative 30i squared. Remember, what is I squared equal to? Negative 1. Remember, I squared is equal to negative 1. So it's not simplified fully until you actually replace I squared with negative 1, and that turns the last term into 30. You can add 32 and 30 to get 60. You can list them all out, add them all up, and combine the like terms. 32 plus 30 is 62. Negative 80i plus positive 12i is going to give you negative 68i. Let's FOIL this one also. When you're multiplying complex terms, you got to FOIL. The first term, 8 times 6 is 48. Outside terms, negative 16i. 8 times negative 2i is negative 16i. Inside terms, 3i times 6 is negative 18i, positive 18i. And the last terms, 3i and negative 2i is negative 6i squared, which gives you positive 6, because I squared is equal to negative 1. So you can write all those out. The first term is 48, 6 is the last term. And the outside and inside terms, they all, when you combine those like terms, you get 54 plus 2i. This number times this number is this number. And how'd you get it? You FOILed. All right, I'm going to cut in here for an alternate ending. Here we go. Right, we got 5 times 3 is, for the first term, is 15. Then we have, for the outside terms, it's 5 times minus 2i to get negative 10i. And for the inside terms, you get minus I times 3 to get negative 3i. And the last terms, you get you get minus I times minus 2i to get 2i squared, positive 2i squared, which actually turns into negative 2 because I squared is actually equal to negative 1. So 2 times negative 1 is negative 2. When you add them all up, you get 15 minus 2 minus 10i minus 3i. Combining the like terms, you get 13 minus 3i. And that's how you FOIL. Let me show you an alternate form to FOIL. Check this out. We're going to accomplish the same thing. We're going to FOIL these, but just in a different layout. And you might say, Berg, how come we need a different way to FOIL? And I'll tell you 2 reasons. The first reason is because FOIL is great because you can, I love FOIL because students across the globe who understand English know the word FOIL and they can remember FOIL, and that's great. But FOIL isn't reversible and FOIL isn't expandable, meaning if I wanted to do a 2x2, then I could use FOIL. But if I wanted to do a 2x3 or a 2x4, I would need more letters than FOIL. So this box method, I'm going to call this, the box method of multiplying is expandable, so we can make it larger. And it's also reversible, as we'll see later. Like I could take these products and move backwards to get this if we needed to. Kind of like this. It's still the same as FOIL, except here's how it works. You're going to have the first terms. This is a completely separate problem. So x times x would be the first terms, and you would multiply x times x and put it here, where you would normally put the f in FOIL, and then x times 2 would be the O term because it's these two right here would be right here, and then x times 1 is where you put the inside terms, and then here's where you put the last terms, FOIL. There's still 4 terms, actually, and you might say, Berg, does it matter? Could I put it x plus 2 over here and x plus 1 down here? No, it doesn't matter at all. The order doesn't matter if you put this one on the top or this one on the side or switch them. So what it would look like is that you put this, you put the -4 plus 2i, say, on the top. You could put it also on the side if you want. They are interchangeable. And then you put the 6 minus 3 on the other side. And then 6 times minus -4 will give you -24. And then -4 times -3i will give you, you put the product here, 12i. And then 6 plus 2i would be 12i here. And then -3i times +2i give you -6i squared, which turns into 6, because I squared is equal to -1. You take all the terms and you can just add them all up right here, and then you get the same answer. Either way you do it. Thanks, y'all. We'll see more of Box method later. And remember, the big idea is if you want to, in order to multiply complex numbers, you got to FOIL, either FOIL or using the Box method. Take care.